Alright guys, so I want to talk about how Newton came up with the idea of understanding how orbit works, how we get satellites, or a natural satellite, for example, like the moon orbiting the Earth. So this is the way he imagined it. So imagine that my little picture here is a representation of the curvature of the surface of the Earth, and that this not to scale mountain here is coming up off the Earth's surface. Okay, so imagine if you took a person up to the top of that mountain and you took a rock and you threw it horizontally off that mountain. All right, we know, you take a rock and you throw it off a mountain, it's going to fall to the ground. So if you throw it, it's going to take a path that looks something like this. Okay, it's going to curve down towards Earth and fall, and it's actually half of a parabolic shape. And if you threw it harder, what ends up happening is that it goes farther away. So maybe it lands over here instead. Okay. What Newton imagined was being in a situation where you launch something so fast horizontally that as it flies out, it does something like this. Okay. So take a look at that picture. You'll notice that all three of these projectiles started at the same elevation. They started at the height of the mountaintop. Okay. And they're all falling downwards. But here's the difference. In the first two, the objects get closer and closer to the Earth's surface and then eventually touch the Earth's surface. But the third one isn't really getting any closer to Earth. Okay? Now my drawing's not perfect, obviously, but the idea here was that you launch something so fast horizontally that imagine in 1 second it falls a certain distance. All right, so imagine it falls this far, let's say, in 1 second. Okay. What he was thinking was, if it moved fast enough horizontally, then in that time, the Earth's surface is actually curving out from under the object by the same amount. So it's not getting any closer to the Earth's surface. So it's falling, but it doesn't get any closer. All right, if that's the case, then it would fall forever around the Earth. That's how we get orbit. So in order for that to happen, you have to have a situation where you launch something so incredibly fast that as it falls, Earth's curvature comes into play and it doesn't get any closer to the Earth's surface. Newton imagined that in order to do this, he calculated out how fast it would have to go, and it turns out that it turns out to be around 8,000 meters per second, so nearly 17,000 miles per hour. Okay, so we're not talking like the speed of a bullet. We're not talking about throwing a baseball. We're talking about something that is much, much faster. And if we were able to launch something fast enough, we could put it in orbit. Okay. The other thing that he recognized, and we're going to see this more in the mathematical part of the video, but what he also realized is that if you were farther away, you wouldn't have to move as fast to maintain orbit. And if you're farther away, the period of orbit is longer because it's a bigger circle and it's a bigger circle and you're moving around it slower. All right, so obviously it's going to take a lot longer to do it. So the period of orbit is a longer period. All right, so we'll develop the mathematics of this a little bit later, but the idea was just that launching something fast enough tangent to the Earth's surface would cause it to be in free fall around the Earth and never get any closer, and that's how it becomes in orbit. Okay, so we were talking a little bit in class about astronauts in space feeling weightless. All right, here's the deal, guys. Gravity's still acting on them. All right, when you're in orbit, gravity is still acting on you. So it's not that there's no weight. It's not that there's no gravity. It's that you're constantly in free fall around the Earth all the time. Okay, so imagine being in an elevator and somebody cuts the cable in the elevator. You're going to feel like you're weightless. You're not actually weightless. Gravity's pulling the elevator and you downwards. But if you took, like, I don't know, let's say you took something out of your pocket and let go of it while you're in an elevator that's in free fall, it's going to float in front of your face because you and the elevator and the thing are all falling at the same rate. So you have this sensation of apparent weightlessness. All right, but it's happening because you happen to be, if you're in orbit, you happen to be falling around the Earth constantly. Okay, so I wanted to talk about some basic concepts behind satellite motion. We already talked about the idea that Newton basically imagined firing a very high-speed cannonball off of a mountaintop, and the fact that it would, if it was launched fast enough, fall around the Earth and not get any closer to its surface. So we kind of had that conversation already, but I want to look more at the mathematics of it. So what Newton realized was that if it's falling around the Earth, it's moving in a circular path. So there has to be a centripetal force acting on it. And that centripetal force, the force that changes the direction of the satellite as it's moving, is gravity. Gravity's pulling on the object and bending its path. So we can write this way. And the two masses in the equation here are the mass of the object, the satellite, and the mass of the planet. And when we look in the centripetal force side, the left side of the equation, we're talking about the mass of the satellite. So the mass of the satellite cancels out in this expression, and we end up with this. We also have an r and an r squared, both in the denominator, so we can cancel this with one of these. And we get v squared equals g times the mass of the Earth divided by r. Or we could say v equals the square root of g times the mass of the Earth over r. So we came up with this expression and recognized that for Earth, if you were close to the Earth's surface, the velocity that would be required would be somewhere around 8,000 meters per second, which is a very high speed and not anything that was attainable at that time in history. He also recognized that it didn't just have to be Earth. It really could be any star or planet or whatever. So we don't need to call it just the mass of the Earth. We could just say that the velocity of a satellite in general is going to be square root of g times m, where m is the mass of whatever you're orbiting around, star, planet, moon, whatever, divided by r, where r is the radius of the orbit. That's very important. It's not the radius of the planet, but it's the radius of the orbit itself. So he was able to recognize this, and this is something we will definitely use in some examples later on. He also recognized, and this is another piece to the puzzle, that if we're talking about a circular orbit, if you remember from circular motion, we said that when something moves in a circle, its speed is 2 pi r divided by the period. And in this case, it's equal to this satellite speed. So if you take those two expressions and set them equal, because they're both equal to v, We can play around with this a little bit. I'm going to square both sides to get rid of the radical. I get 4 pi squared r squared over t squared equals gm over r after squaring both sides. So what I'll do now is I'm going to actually isolate r in this expression. So I'm going to multiply by t squared. I'm going to divide by 4 pi squared. So what I end up with is this. And take a look at that expression for a minute. It should look sort of familiar. I have r cubed on the left, and I have t squared on the right. If you remember, Kepler had said in his third law that the cube of the mean distance from the sun is proportional to the square of the period. That's what this is saying. Because all of these numbers, g, m, 4, and pi, are all constants. So we have a one big giant constant that I circled there, times t squared equals r cubed. This is basically Kepler's third law, and this is one of the ways that Newton knew that his law of gravitation was legitimate, was because it predicted Kepler's third law. So these are both things that are useful to us and helpful for analyzing the motion of satellites.